The leaning ladder. A uniform ladder of length L rests against a smooth vertical wall. So we have a uniform mass distribution, uniform ladder. So the center of gravity should be in the middle. It rests, so it is at rest. We have static equilibrium, a smooth wall. There is no friction between the ladder and the wall. The mass of the ladder is m, and the coefficient of static friction between the ladder and the ground is mu s 0.4. Find the minimum angle, theta minimum, at which the ladder does not slip. So you can see that it is leaning against the wall. There's no friction here, but there is friction between the ground and the ladder. We're trying to find the minimum angle theta for the ladder to not slip against the wall. And if you look at the forces acting on the ladder here, you can see we have, because it's a uniform ladder, center of gravity is in the middle, we have mg pointing down. We have this normal force from the ground pointing up, and we have static friction that is basically opposing the contact force on the wall. So it's between the ladder and the wall. We have a contact force P that is pointing to the left, static friction is pointing to the right, and we have equilibrium. Okay, so let's start with noting that we have the ladder at rest, and therefore we must have static equilibrium. And the second thing to note here is that the vertical wall has no friction. Okay, so we can write the static equilibrium conditions. So translational equilibrium requirement, if we have a coordinate system set up like this, x is the horizontal axis, y is the vertical axis, z is coming out of the page, the net force x component must be 0. So this requirement implies that since I have static friction pointing to the right, the contact force pointing to the left, I will have Fs minus P in I hat direction should be 0. Therefore, the static friction must be balancing the contact force from the wall. The second equation is for the y components of the forces. The net y component should be 0. So I look at the forces that have a y component. There is the normal force, there is the weight pointing down. So normal force is pointing up, the weight is pointing down, and minus mg j hat should be 0. This tells me that the normal force is balancing the weight of the ladder. Okay, so let's remember the behavior of static friction. Static friction is normally equal to the applied force. It's balancing up to a maximum value, which is mu s times the normal force, and then it quickly goes down to kinetic friction, which is mu k times the normal force, at a critical force magnitude. That's the critical p value here. This is where it's at the verge of slipping. Then it starts slipping, so it is moving with under the influence of kinetic friction. So we see that the maximum value of static friction is coefficient of static friction times the normal force, and I have found from the translational equilibrium requirement number 2, that n must be equal to mg. So mu s times mg is equal to the critical value of the contact force on the wall. And now let's write the rotational equilibrium requirement. The rotational equilibrium requirement is that the total torque, external torque, should be 0 about an axis, about any choice of rotation axis, but I'm going to choose point O. Why? Because I have two forces there, normal force and static friction. So I will eliminate these two forces from my equation because they don't have a torque effect with respect to point O. So I'm choosing this as my rotation axis. So it's about an axis going through point O. All right. So let's write this torque. Now, the weight of the ladder will have a contribution here. You can see that it has a perpendicular component mg cosine theta. So if this angle is theta, 90 degrees, 90 minus theta, this will be theta. And on the other hand, we have this contact force P here with the wall. So you can see that this angle it makes with the ladder is also theta, and it will have a perpendicular component P sine theta that will have a torque effect. P cosine theta goes through the pivot point, so it doesn't have a torque effect. Okay, so using the right-hand rule, I can see that if I go from the pivot point to the application point of the force, and then follow the force with my right hand. So my fingers point from point O to the center, curl them towards the perpendicular component of the weight. My thumb points into the page, so this creates a torque in minus k hat direction, and this creates a torque in plus k hat direction. So if you go from here to here, and you can see your thumb will point out of the page. So I have mg cosine theta. Now, what is the perpendicular distance between the pivot point and the application point of the force? That is L over 2. L over 2 in minus k hat direction. And then I have P sine theta. The perpendicular distance is now L in plus k hat direction. This should add up to 0. Okay, so this is basically telling me that mg divided by 2 cosine theta must be equal to P sine theta. Why? Because these L's will cancel. Okay, so I divide both sides by L, and this P has a critical value mu s times mg, so it's mu s mg sine theta, and you can see that these mg's will disappear, and I will be left with a tangent theta here. So tangent theta, sine theta over cosine theta, will be equal to 1 over 2 coefficient of static friction. So the minimum angle theta, which has the critical value of P, mu s mg, is basically tangent inverse 1 over 2 mu s. Okay, so this is my symbolic answer. Now, if you plug in the numbers, that's tangent inverse of 2 divided by 1 divided by 2 times 0.4. That was our coefficient of static friction, 0.4. And this gives us 51 degrees as the minimum angle I need to have static equilibrium without the ladder slipping. Okay, so in this problem I had a ladder that is leaning against the wall making an angle theta with the horizontal and being subject to friction with the ground but no friction with the wall. So first we identify the forces acting on it. The normal force from the ground, static friction pointing to the right, which is balancing the normal force from the wall. That's P pointing to the left. And because it's a uniform ladder, we have center of gravity in the middle, mg pointing down. So we write the translational equilibrium requirement. The x component of all the forces should add up to 0. That is Fs minus P is 0. The y components, the normal force minus mg should be 0. The static friction has a critical value μs times n when the P reaches its critical value, P critical. That's the maximum value of static friction, which is μs times mg. And as for the rotational equilibrium requirement, my choice of the rotation axis is point O. The pivot point is point O, so that I eliminate the normal force and Fs having any effects on this torque. So only mg perpendicular component and the contact force P perpendicular component will have a torque. So writing this torque equation and substituting for P μs times mg, I find the minimum angle tangent inverse of 1 over 2 μs or 51 degrees. Now let's look at another example. Estimate the magnitude of the force F a person must apply to a wheelchair's main wheel to roll up over a sidewalk curb. This main wheel that comes in contact with the curb has a radius r and the height of the curb is h. And determine the magnitude and direction of r, that's the contact force. So we have a person going over a curb here, in the sidewalk. You can see that we have a force being applied on top of the wheel to the right. There's a horizontal force. The wheel has a radius r. So if the sidewalk has a height of h, we can see that this force is applied at a perpendicular distance to point A, the contact point with the curb, at 2r minus h. So r minus h is the distance between the center and point A, the perpendicular distance. Now, as for the forces acting on this wheel, we have F, the force being applied by the person. It's a uniform wheel, we assume, so we have center of gravity right in the middle and mg pointing down, and then we have a contact force between the curb and the wheel that is, let's say, at an angle theta with respect to the horizontal. We call that r. So these are the three forces acting on the wheel. Okay, so if we concentrate on this OCA triangle, we can see that this is a right triangle. All right, so let's make this a bit smaller. Here's 90 degrees. Okay, so from this triangle, OCA triangle, the Pythagorean theorem tells us that r squared is equal to hypotenuse squared is equal to r minus h squared plus d squared, where d is the distance between point B and point A. So you can see that this is d. So d is equal to r squared minus r minus h squared square root. And we have this just at the verge of rolling up. That means we have equilibrium. So just at the verge of rolling up, that is equilibrium. So for static equilibrium, we have x components should add up to 0. So if I look at the x components of these forces, there is F, and r cosine theta is in the opposite direction. So it's F minus r cosine theta I hat should be 0. That means the force F is equal to r cosine theta. The net force, external force y component should be 0. Now the y component comes from mg, the weight, and the y component of r. So since at this point we are losing contact with the ground here because we are at the verge of rolling up, the normal force that would be normally applied on the wheel will go to 0 because we are losing contact here. Okay, so we have r sine theta, the y component of r, minus mg, j hat is 0. Therefore, r sine theta must be equal to mg. So if we divide these two equations, r sine theta divided by r cosine theta, that is tangent theta, this must be equal to mg over f. So we're dividing the y equation by x equation. And for the rotational equilibrium requirement, the net external torque should be equal to 0. We're going to choose a pivot point here, and since I want to eliminate this force R, I'm going to choose the pivot point at point A. So as you know, we have freedom in choosing the pivot point. So writing the torque with respect to point A, now you can see why I calculated this d here. I have to find the perpendicular distance between mg and the pivot point. That perpendicular distance is d. And similarly, I need the perpendicular distance between the application point of this force F and point A, that is 2r minus h. So writing the torque here, mg times d, the perpendicular distance. Now I can determine the direction of this torque with this coordinate system. I go from the application, from the pivot point to the application point of the force. I curl my fingers towards the force and my thumb point out of the page. So it's going to be mgd k hat. But for the force F, if I go from the pivot point to the application point of the force, curl my fingers towards F for the right hand, the thumb points into the page, so it's going to be minus F 2r minus h k hat. And this should be equal to 0. That's a equilibrium requirement. I'm going to substitute for d this result. And also I will get rid of the k hats here. So this will give me mg r square minus r minus h square. Square root, that's d. This must be equal to f times 2r minus h. So I have found f, the force the person must apply, to be mg r square minus r minus h square, square root divided by 2r minus h. Okay, so that's the force the person must apply, the minimum force actually they must apply. The person must apply, so that we will be just negotiating this curb, losing contact at point B. The normal force goes to 0, and we have just established equilibrium at the verge of rolling up. Then we can find theta. theta, the angle this contact force R makes with the horizontal is tangent inverse of mg over f. So it's going to be tangent inverse of mg over f. So for f, I substitute this result. So mg times 2r minus h divided by mg times r square minus r minus h square, square root. These mg's will disappear. So the angle theta with respect to the horizontal axis for r will be tangent inverse of 2r minus h divided by r square minus r minus h square, square root. So that tells us the direction of r. The direction is to the left, making an angle of theta with respect to the minus x direction. So it's this angle. Then I can find the magnitude of r. What is the magnitude of r? Well, I can use this equation or this equation. It's mg over sine theta. So I can say that this is mg divided by sine theta. And then I can substitute my result for theta, so that r magnitude is mg sine of theta, which is tangent inverse 2r minus h over r square minus r minus h square, square root. That's the angle. And the sine is at the bottom here, it's in the denominator. So sine theta with a power minus 1. So this should be the magnitude of the contact force with the curb. Okay, so in this problem we have looked at the critical condition for negotiating a curb. We want to estimate the magnitude of the force a person must apply horizontally to the wheelchair's main wheel to roll up over a sidewalk curb. And we know that it has radius r and the height of the curb is h. And we want to know the contact force r with respect to the between the wheel and the curb. So first we have written, we have looked at the vertical distance with respect to this pivot point A here. So that's the choice I have in order to eliminate the two unknowns theta and r from my equations, the torque equation. I see that this perpendicular distance is 2r minus h. This perpendicular distance between the weight here and the center of gravity and point A is d, and that can be found by using this triangle which has sides r minus h, d, and hypotenuse r. Now I have written the translational equilibrium requirement. The net force on the x-axis should be 0. I look at the forces acting on this wheel because I'm just leaving this ground contact point here. I will basically have no normal force acting on it, and at the same time I have the center of gravity in the middle, mg, pointing down, and I have this force F pointing to the right. That's the force applied by the person, and contact point R. And F and R cosine theta are the x components, mg and r sine theta are the y components. So writing the x and y translational equilibrium equations, I obtain tangent theta is mg over f, and r sine theta is mg, or r cosine theta is f. And the torque with respect to point A, the only two forces are mg and f that have a torque effect with respect to point A. So mg dk hat, the perpendicular distance, using the right hand rule, I see that the torque is in k hat direction, and for F it is in minus k hat direction, but the perpendicular distance is, so the distance here would be 2r, but I have h here, so it's 2r minus h. So from the torque equation I obtain F. Then I substitute F into tangent theta equals mg over F equation. I obtain theta, and R equals mg over sine theta, or I can use R equals F over cosine theta. Substitute this result for theta, and I find the magnitude of this contact force R.